All right, we're going. All right, so something new at the top. It's still almost 2 weeks out. Just to give a heads up. We have our second exam coming up on the 25th. Schedule will all be the same, right? So the Monday exam in class, and then the online portion will be from after class, or Wednesday, and then Wednesday, Friday, second attempt. I have set up that exam, so if you're really eager to get set, a time schedule, you go ahead and do that with the testing center. The other thing that I didn't write on here is I know that I had heard from several of you that every time you go and connect, it's telling you that your subscription is expiring and please pay more money. So don't do that. Okay, we had this problem at the beginning of the semester, and it was supposedly resolved, but now it's popped back up. I have been in contact with publisher, and they have assured me that they will get it worked out. Okay, so do not pay them more money. Okay? Huh?
We just started doing deactivating.
Oh, really? Oh. Yeah. Okay, so did you hear that? Some people, it says renew, they just hit renew, and it just renewed, but it didn't ask for money. Okay, so try that. Okay, thank you. Okay, so we are in chapter 18. We have just learned first about a series, let's go down, series of electrophilic substitution reactions. We then spent time on Monday talking about reactions that we could use to modify substituents once we put them on the ring. So we had several modifications for alkyl groups if we put those on the ring. We had a modification for a ketone that's next to the benzene. We could reduce that to the alkyl group. And we talked about the reduction of a nitro group to what kind of functional group we get. And then amine. Okay? So what we're going to do now is we're going to move forward. We're going to talk about what happens if we have one substituent on the ring and we want to add a second group. All right? So then we have to consider two different general things. First is whether that substituent on the ring is going to make the benzene ring more active or less reactive. And because when we add a second group, we can have different orientations. We can have groups that are ortho, meta, or para. And so maybe this certain group will direct the second group to a specific position. Okay? So those are the things we need to now talk about. All right? All right, let's do a clicker first, though. All right, so far, just to list out what we've been doing already. I've kind of highlighted all this already, but we've learned about electrophilic aromatic substitution reactions. We did these 5 reactions, and then we looked at how to modify substituents onto the benzene ring. So right now, we're going to look at these substituents and try to learn whether they're activating or deactivating. So an activating group is going to make that ring more reactive than benzene. A deactivating group would make it less reactive than benzene. Once we've done that, we will consider different substituents and look at whether they will direct the second group to a specific orientation, so ortho, meta, or para. Okay? Here to learn how to synthesize substituted benzenes, we've already learned to attach one group, we know how to modify them, and now we are adding our second group. Okay? So let's think about these two things. So the first thing is, how does their reactivity compare to benzene? and next will that group go ortho, meta, or para. So let's first think about the reactivity issues. All right? So for a simple point of view, I think that works out here, we can look and categorize our different groups. This EWG means electron. I'm going to switch colors here. Withdrawing group. Okay? So what role does the benzene play in this electrophilic substitution reaction? Is it the electrophile? No. It's the nucleophile, right? So a nucleophile is going to be increased in its reactivity if it has more electron density. Right? The more electron density in the ring, the more nucleophilic it will become. All right? So if we put an electron withdrawing group here, which is going to pull electron density away from the ring, is that going to make it more reactive or less reactive? This should cause it to be less reactive. Okay? So this would be a deactivating. Deactivating. All right. So if we have over here an electron donating group, so it's going to be pushing electron density into the ring. Is that going to make it more or less reactive? More reactive, right? Because we're loading up electron density. We're going to make it more easy for that benzene ring to donate electrons, right? So this is going to be more reactive. And so we call it an activating group. Okay, so these are all relative to benzene, which is in the middle. Okay? So what we have to do is be able to look at various substituents and be able to decide or determine whether they are electron donating groups or electron withdrawing groups. Okay? All right, so again, here's just our standard that we're comparing everything to. All right, so what do you think if we put on this methoxy group? So we have an ether here. Is that going to be electron donating or electron withdrawing? Okay, so oxygen is more electronegative than carbon. Right, so it will be pulling electron density out like this. So electron withdrawing, and what kind of a process is this, I guess? Is this electron withdrawing through resonance or inductive effect, or what type of electron withdrawing is this? Yeah? It is the electronegativity, so that's what makes it the electron withdrawing group here. So when we have only a sigma bond through there and we have a difference in electronegativity, what mode of electron withdrawal is that? That's the inductive effect, okay? Drawing electron density through a sigma bond. Okay, so this would be electron in drawing through an inductive effect, induction, I guess I could say. Is that the only thing that methoxy group can do? Yeah, it also has a non-bonding pair of two non-bonding pairs of electrons, and these electrons can be donated into the ring. Okay, so this is an electron donating effect. Okay, so it can also be electron donating. and this is through resonance. All right, so we have two things that are like conflicting, right? This molecule is just conflicted. All right, so which of these two things do you think wins out? Induction? How many people think the induction? Okay, how many people think resonance? Resonance it is. We're just a democratic class here, and the properties of these molecules is just decided by you. So it turns out that it is the electron donating. I think in general, resonance effects are oftentimes stronger than inductive effects. Okay? So this methoxy group will act as an electron donating group. And so is that going to be an activating group or deactivating? Activating, right? It's pushing electron density into the ring, increasing the electron density, making it a stronger nucleophile. Okay, so we could say that this is activating. All right, next one. We have a nitro group. So what do you think? Activating? Well, let's not do that first. Let's think about what modes of electron donating or withdrawing could that nitro group have? Anybody? Well, it has this plus on the nitrogen right next to the ring, right? So what do you think that's going to do? It's going to withdraw electrons, right? So it's going to withdraw electrons like this through induction. Can the nitro group participate in resonance? Yes, right? These electrons could go up on the oxygen, and that's going to pull electrons from the benzene ring. Okay, and so this part of it is resonance. All right, notice that both of these effects now are working together, right? They're both pulling electron density out of the ring. Okay, so a nitro group is a very strong electron withdrawing group. Okay, and so it would be a deactivating group. Okay, what about the next one? What about the nitrogen there? The aniline, the amine. It can donate with the lone pair. That's true, right? So we have a lone pair here, can be an electron donating group by resonance. It also withdraws electrons by an inductive effect because it's also more electronegative than carbon is, right? And so this is essentially a situation very similar to the oxygen over there. Okay? In fact, nitrogen is less electronegative, so it's less withdrawing, and it's actually a better donating group. Right? So this is a strong activating group. Okay, so this is going to be activating. So it's essentially like the OCH3 that we already did. Okay? All right, let's go to the bottom left. We have, this is an amide functional group. Okay? What effect is that amide going to have? Okay, how can it affect the electron density in the benzene ring? Yeah, so it also has a non-bonding pair of electrons here. Right? So it can donate electrons like this. Do you think it's going to be as strong of an electron donating group as the amine up here? No, why not? Right, because it can also have resonance with the carbonyl. So this pair can also have resonance over this way. Okay? So this lone pair is also conflicted, right? It has mixed responsibilities here. Okay, so, and the nitrogen again is more electronegative than carbon, so it has some electron withdrawing group by induction. This is an activating group. But it's a little bit less activating than the amine is because it has that extra resonance going away from the ring. Okay? All right. Okay, this is less strong than the amine. Okay, what about if we have a ketone next to the ring? Deactivating, so it would be electron. What's this going to do with the electrons? Withdrawing, right? So another way that, well, so it's going to go this way. Here, let me draw out another way that the book kind of, well, we can do that afterwards here. So it's going to pull electron density this way. Essentially, just in the same way as we drew for the nitro group. Okay? So through resonance, it's pulling electron density away in the same way. This also has a resonance form, or contributor, or structure, that would just use those top electrons that would have a structure like this, right? So if all we do is, let me use a little pointer here. If we only use these electrons here, if we just take that carbon-oxygen double bond and we bump it up onto the oxygen, then we're left with a plus next to the benzene ring. And so that plus there also shows us that we would have an inductive effect here as well, right? Because we have a plus group right next to the ring. So this has both resonance and inductive effect that are withdrawing from the ring. It doesn't have a full plus like the nitro group, but this is an electron withdrawing group. It is going to be then what? Activating or deactivating? Deactivating. All right. What about the halogen? Okay, it is more electronegative, right? So it can pull electron density away inductively. Can it act as an electron donating group? It has electrons on it, right? It has, let me get my little lines. Oh, I can't do that. It does, oh, I did. It does have 3 pairs of non-bonding electrons that can donate in like this. Right? So it can do both. Turns out that halogens, we'll talk about this a little bit more in a minute, end up being kind of a unique group. Okay? But based upon these things, the actual withdrawing is a little stronger, and so these are these are deactivating. Let's just put it that way. Right? Even though they can withdraw, they can also donate some electron density. So in this case, we have these two conflicting effects. You know, when we had the amine or we had the oxygen, the ether, we had the same conflicting effects, but the donation was stronger, so they were activating groups. Here, with the halogen, the donation is not as good, and it's the electron density, the electronegativity, the inductive effect becomes stronger. Okay, so it ends up being deactivating. All right, so what about if we just put a alkyl group on the ring? Is it going to change it, or is it going to be just like benzene, or is it... So let's think about it. So what is another type of species that we've looked at, reactive species maybe, that is its stability is affected by having alkyl groups around it? So like a carbocation, right? By adding alkyl groups around a carbocation, does that make it more stable or less stable? More stable, right? If we have a carbocation, is it going to be more stable if we donate electrons to it, or if we try to pull electrons away from it? Donating to a cation makes it more stable, all right? So if we follow the same reasoning, then a methyl group or an alkyl group should be electron donating, right? Because they can stabilize carbocations. So in fact, these are, alkyl groups are electron donating, weakly though, and so it should be activating. The other way that you can think about it is that this carbon is sp2 hybridized, right, in the benzene ring. What about this methyl group carbon? sp3. So what do you know about how hybridization affects electronegativity? Yeah.
sp2 hybridized orbital is going to have more s character, and the s orbital is closer to the center of the nucleus, so it's going to pull electrons.
Exactly. This is exactly. You probably not everybody heard all that, but as we increase the amount of s character, right? sp2 is 33% s, whereas sp3 is only 25% s. As we increase the s character, because that s orbital is closer to the nucleus, it pulls the electron density closer to the nucleus, kind of translates to being more electronegative. Okay, so in this case, which is different from all these other ones, we always put a more electronegative group on the ring, but in this case the ring is more electronegative. So the electron density is going to be going towards the ring, right? Going towards the more electronegative side. All right? Yeah?
So when we're talking about activating versus deactivating, are we talking about the subgroup is being activated to be more reactive, or like how does that?
No. Okay, so the question was, what do we mean when we're saying activating and deactivating? In each case, we're talking about the reactivity of the benzene ring towards an electrophilic substitution reaction. Okay? And remember that the rate determining step for that reaction is the ring, or the pi electrons in the ring reacting with an electrophile. So the more activated it is, the more electron density it has, so it can donate those electrons in that step. Okay, so it's all about the reactivity of the benzene ring and how it's being influenced by the substituents. Okay? So let's substituents here. And this is kind of divided up into activating groups and deactivating groups. Okay, so notice the line in this part of it goes to right here. Right? Up here are the activating groups. All of them, except for the alkyl groups, all have some functional group that has a non-bonding pair of electrons on it. Whether it's an amine, or a OH, or an ether, or an amide, or it could be an ester. They didn't put that one in there. It could be oops, oh, don't let me do that, like this, right? So it's still an oxygen attached to the benzene ring. So all of these have this kind of atom that's attached directly to the benzene ring that has non-bonding electrons that can be donated, okay? The alkyl group we talked about, it's not as strong of a donating or activating group because it doesn't have that pair of electrons, but it still donates some electron density inductively. All right? These bottom ones from here down, okay, all of these have some group attached to the benzene ring that is either plus, excuse me, like the nitro group had a plus on that nitrogen. If we have an ammonium ion that has a plus, full plus on that nitrogen, or it has some atom attached that has a delta plus. Okay, and that's true of all of these carbonyls. Okay, in each of those cases, excuse me. I'll just put a Y group over here. In each of these cases, we have a resonance structure because of that polar carbon-oxygen bond that has this resonance contributor that has a plus on it. So that gives us a partial plus on the carbonyl carbon. Okay? Now the unique ones here, like I mentioned, are the halogens, all right? And so they are, in fact, included into the deactivating groups, even though they have non-bonding electrons on them, okay? So they're unique. Okay? So this is activating and deactivating. So the next thing we have to decide, though, is if we're going to have one of these groups on it, how is it going to affect the position of the next group that goes on to the ring? Let's pick kind of one of our prototype activating group. Okay, so this methoxy group. And what we're going to do, we're going to work out a big thing here where we're going to look at what the intermediates would be like if we put the electrophile on the ortho position, the meta position, or the para position. And we're going to evaluate the stability of those intermediates. Okay? All right, so first we're going to put it on the ortho position. Okay, so I'm just going to draw this out like this. OCH3. I'm going to put the chlorine here. Had the H there already. And no, I don't want that there. Let's put the plus. I'll just do it so what we're doing is this reaction essentially here with the electrophile, not with chlorine itself, right? Chlorine first reacts with iron chloride to make the electrophile. So if we did that, then we'd end up with a plus here, and a double bond here, and a double bond here. Okay? So remember, each of these intermediates are stabilized by resonance, right? So we have each one, we'll draw some of these out, has the same type of resonance. Let's see, I don't want that. Right, so if we draw another one here, we have the Cl up here, the H over here, OCH3. We shifted the double bond there, and now we have the plus at this position. Right? We could do this one more time. These electrons could move down this way. So these are all kind of the standard resonance structures that we draw before, and so far they aren't any different than if we didn't have this methoxy group attached. Okay, that would put the plus over here. All right, so is there anything else that we can draw that involves that methoxy group? How is that methoxy group going to influence the stability of this resonance stabilized carbocation? Yeah.
Couldn't the oxygen itself take on the positive charge by donating electron groups to the ring?
Yeah. So the suggestion was that we know that this oxygen has non-bonding electrons on it. Okay? And we know that this oxygen can have two different effects, right? We know that it's electron withdrawing by induction, right? Would that stabilize that cation if it was pulling electron density away from it? No, that would destabilize it. But we know that it can also donate electrons through resonance. So let's do that. I'm going to take these pair of electrons and I'm going to donate it over toward the plus. This is going to give us another resonance structure. It puts a double bond to the oxygen now, and the plus on the oxygen. Okay? So what do you think about that resonance structure relative instability to the other three? More stable? Why is it more stable? It has what? It has the most bonds, that's true. It has the most bonds, and the other thing that it has is that it has all of the atoms that are not hydrogen, all have complete octets of electrons. All right? So in fact, we've not only added an extra resonance structure, we've added an extra one that's more stable than all the others. Okay? So we have this extra resonance. All right? So let's see if that's the same in every case. All right, so the next thing we're going to do is we're going to put that chlorine on the meta position. Okay, so I'm going to put here's our chlorine, and there's an H there, and then I'm just going to do it from the structure up there, so this is going to put the plus over there, and we can get to this resonance. Okay, so let's look at the other resonance structures that we can draw. Okay, so like before, we can bump this over towards the plus. We have the chlorine and the H there, with the double bond there, there. Puts the plus here. Okay. We can do this one more time. Move that double bond over there. So are we going to be able to put the plus out onto the oxygen in this one? No, because the way this resonance works, the plus is going to just jump right past the position where that methoxy group is. Right? Because the plus only gets to land on every other carbon when we're doing this kind of resonance. All right, so then we get the plus here, here. Okay, we get to here. So these are the only three that we can draw. We don't have any extra ones in this case by having the methoxy group there. Okay? So what do you think? This middle one versus the top one, which one's more stable? The top one is more stable so far. All right? Let's, we got to finish this whole thing out. Let's put the chlorine on the para position. Okay? And let's see what happens then. OCH3 here. I'm going to put chlorine over here. I'm going to put the plus right there. And we get our intermediate. Okay, so now let's do our resonance. This goes over here. Right, so that's their chlorine H plus. All right, we can do it one more time. Here, plus down here. So these are the same three that we always have. All right, so can we draw an extra resonance structure for this intermediate? Yes, where would we draw it from? From the middle one here, right? Notice that in this middle structure, it has the plus right on the carbon where the methoxy group's attached. Okay, so then we can take a pair of electrons from that oxygen, we can donate them down to the ring, and we can draw one new resonance contributor, resonance structure. Right, so this has this, OCH3 plus. Okay, so again, in this bottom, when we put that chlorine para, we also have this extra resonance. All right, so let's just write it out this way. So we could have, this is para, this is meta, this is ortho. Okay, so a methoxy group, a strong activating group, a strong electron donating group is going to favor para and ortho. Okay, so we call it an ortho-para directing group. Yes?
So in the original reaction mechanism, that H that was on the same position as the Cl ended up getting removed, and it went back to a benzene ring.
Yes.
Why does that not happen to you?
It will. So the question was, before we always talk about another step where the H is removed. That would happen. We're only looking up to the intermediate though. Okay, so from these intermediates here, we could get to that product from any one of these intermediates. Okay, so what would happen is our base, or the iron tetrachloride anion, would have that Cl would remove a proton, those electrons would go into the ring, and electrons would go back up on the methoxy group, and we get to our product. Okay, so we're just looking at the rate determining step here. Okay, good question. All right? Okay, so it's an ortho-para direct. Do this whole thing for the nitro group, right? Super fast. Okay, we can't do that now, but tomorrow we will do that. Okay, so we'll look at what the effect of the nitro group is.